Hi all. So today we'll discuss on a topic that is synchronous motor, the types of motors, application, and rotating magnetic field. So on completion on this session, you could able to know the classification of AC motors, comparison with a synchronous motor, and what is an AC motor, and applications of AC motor, and advantages and disadvantages of AC motor. Though we may not have in syllabus that AC motor, but we would know the AC motor so that we could able to get an idea. Okay. And what is rotating magnetic field, how it is produced, and generation of three-phase rotating magnetic field, mathematical proof for production of a rotating magnetic flux. So this rotating magnetic field, we have already used this word in induction motor, and we will see how actually the rotating magnetic field has been produced. So what is this picture? Yes, this is an electric motor. And a motor is a device which converts an electrical energy into a mechanical energy. And how many types of electric motors are there? AC motors. In AC motor, synchronous motor. So synchronous motor. So here we are much concentrated on the synchronous motor. One of the type of AC motor is a synchronous motor. So here synchronous motor is a constant fixed speed by system frequency. So here the synchronous motor will rotate at a synchronous speed, at a constant speed, and it need a DC for excitation and low starting torque suited for low load applications and can improve power factor suitable for high electricity use systems and synchronous speed is NS. So these are some of the uh, characteristics we can say of a synchronous motor. Okay, and synchronous speed that is ns is equals to 120 f by p, where f is a frequency and p is the number of poles. So synchronous motor, it is just as a DC generator and can be used as a DC motor. So AC generator or alternators can be used as synchronous AC motors. Three phase motors use three sets of stator coil. So here the rotating magnetic field drags the rotor around with it. In single phase motors require some starting mechanism. Torque is only produced when the rotor is in sync with the rotating magnetic field. It is not a self-starting motor, may be configured as an induction motor until it gets up to speed. Then it becomes an synchronous motor. So it is not a self-starting motor, and we know that induction motor it will run by its own, whereas synchronous motor is not a self-starting motor, so we have to run it. So there are some starting methods. So here we are running it as an induction motor for some extent. After attaining a certain speed, then we are removing an induction motor topology, and then it will run as a synchronous motor. So this is a synchronous motor, stator, and here rotor we have. So synchronous machine employs to convert electrical energy into mechanical energy. To present the principle of a synchronous motor, a two-pole synchronous motor considered, and it has some basic speed, power, torque equations as synchronous generator. So T is equals to K into BR into BS, which is a counterclockwise direction. That is, and synchronous motor is the same in all respects as synchronous generator, except then direction of power flow. Since the direction of power flow reversed, direction of current flow in stator of motor may also be reversed. Therefore, its equivalent circuit is exactly as synchronous generator equivalent circuit, except that the reference direction of IA is reversed. So AC motors. AC motors are very popularly used in day by day life and practice, and AC motors are those can be operated on AC supply. So how many types of AC motors are there? And AC motors are classified according to different factors. That is, according to the principle of operation, according to the speed, and according to the type of the current, according to the structure, and according to the location. So, according to the working principle, AC motors are synchronous motors and asynchronous motors. And according to the current, it is single phase and three phase AC motors. And the AC motors are classified according to speed, that is, constant speed, adjustable speed, and variable speed. And AC motors are classified based on structural features, that is, open type, closed type, and semi closed type. And classification according to the location, that AC motors are classified as surface type and submersible type. So, a synchronous motor, it is a constant speed motor and it can be operated over a wide range of power factors. It is a doubly excited machine and it is a variable speed motor, that is induction motor, asynchronous motor. Okay, you have to note down the differences of their characteristics. And as induction motor, that it works with lagging power factor only. So what are the advantages of the synchronous motor? Here, the power factor can be controlled easily and motor can work at lagging power factor, leading power factor, and unity power factor. And speed is constant and it is independent of load. Though you have put lot of load on a synchronous motor, the speed of a synchronous motor is constant. It does not change like an induction motor. But yes, it has two stages. Either it will rotate it at an synchronous speed or else it won't rotate. So, if for example, if the load on a motor increases, it is it has been overloaded, then what happens? It directly uh, a synchronism will lose, hence the motor won't rotate, it will stop. And what are the disadvantages of the synchronous motor? The first most disadvantage is that it is not a self-starting motor, due to which we need a separate motor for starting it. So it requires a DC excitation. Initial cost is very high and it cannot be used for variable speed drives as it is a constant speed motor. And if the motor is overloaded, it may fall out of step. It has a tendency to hunt. So these are the disadvantages of the synchronous motor, and we'll see the applications of a synchronous motor where it has been applied. So it can be used as a power factor corrector and constant speed applications like clocks, air compressors, and centrifugal pumps. So improving voltage regulations of long transmission lines also it is used, and it can be used at a frequency changes. So these are some of the applications of a synchronous motor where it is used. So now we will see the generation of a three-phase rotating magnetic field or flux. Okay. So here the rotor construction of the synchronous motor is same as that of an induction motor stator construction. Okay. So here when three-phase distributed winding placed by 120 degrees is excited by a three-phase balanced supply, then it produces a resultant magnetic flux rotating in space as if actual magnetic poles were being rotated mechanically. So this is a stator. Okay. Here to the stator we are giving a supply, a three-phase supply. So this is one phase, and here one more phase, and here one more phase. So R by B type. Okay. So we are giving the three-phase supply to the stator. So R, Y, and B. So when we gave a three-phase supply, then the currents will flow, that is three phase, each 120 degrees apart. So the current which is flowing in a conductor, stator conductor or the winding will produce the flux in the same direction like this. Say this is a flux now. So this is a pi r flux produced due to the IR, and this is a pi y flux produced due to the IY, and this is a pi b flux produced due to the IB currents. Okay, so here if we see where the diagram angular distance between each and every phase is 120 degrees apart. Okay, so here after starting of pi r, pi y has been started, and then pi b has been started. Okay, so in the x-axis the angle representation has been given, and in the y-axis that is the pi has been taken. So pi r, so we know the current if it is IR, that can be written as I maximum into sine theta. In the same way here we have written pi r is equals to pi maximum sine theta, pi y is equals to pi maximum sine theta minus 120 because after 120 degrees it has been started, and pi b is equals to pi maximum sine of theta 240 because after 240 of initial point it has been pi b has been started. Okay, so this is a vector representation. So pi r after 120 degrees pi y, and after 120 degrees from pi b it is, so after 120 degrees of pi y it is pi b. So each and every flux has been taken 120 degrees phase shift. So this is a vector representation. So now we know the vector representation and also the actual diagram in sinusoidal form. So here, so at each and every point, say this is 0 degrees, at this is at 30 degrees, this is at 60 degrees, this is at 120 degrees. So likewise, so case one, when For example, when theta is equals to 0. At theta is equals to pi r is 0. Yes, you can observe here at pi r is equals to 0. And pi y, which is equals to pi maximum sine of theta minus 120. This will be 0. Theta is 0. So which is equals to sine minus 120, which is equals to minus pi maximum sine of 120, which is equals to sine 120 is minus root 3 by 2. So minus root 3 by 2 pi maximum, and pi b is equals to pi maximum sine of theta minus 240, which is equals to minus pi maximum sine of 240, which is equals to root 3 by 2 pi maximum. So here if we observe one of the one of the pi value is 0 and the other two, that is, oh, cat కి నిద్ర వస్తుంది, మీరు పడుకోరు పిల్లలు, అది పడుకోద్దా? మధు. So here we have seen already a vector diagram. So at the theta is equals to 0 degrees, pi r is 0 and pi y is pi y is minus root 3 by 2 pi maximum and pi b is root 3 by 2 pi maximum. So here this pi r is 0, so only the two fluxes are pi y and pi b. So if we see here, this is a pi y and this is a pi b. So both magnitudes are same, but it is in opposite direction. Okay, fine. So how this vector actually has come, we will see. Okay, so here this is pi b, pi pi r. So this will become minus pi r value. Okay, direction I just have drawn in a short form. Okay, and this will become minus pi by, and this will become minus pi b direction. Okay, so here at theta is equals to 0 degrees, this point. Okay, so we know that the pi r is 0, so this is 0, this is not there. Okay, and yes, now pi y is minus root 3 by pi m. So where is the pi y? Pi y is in this direction, so it is telling, so in the same negative direction we have to take. So in the same negative direction, it is the direction, this is due to the minus direction, and the magnitude is root 3 by root 3 by 2 pi maximum. Okay, and here pi b is root 3 by 2, it is positive only. So here this will become root 3 by 2 pi maximum. Okay, so now we have to find out the resultant resistance. So resultant resistor will fall in between these two, because both are in the both the magnitudes are same. Okay, but what is the magnitude of this? These we need to find out. So here this is 120 degrees from here to here, then this will become 60 degrees, and this will become 60 degrees. Okay, so we have to find out this part. So we will see. So therefore the resultant is, so here pi r is equals to 2 into root 3 by 2 pi maximum into cos of 60 by 2. Okay, so that is why, so here 60 will become 30, right? So because of that only it has given 60 by 2. That means it is 30. So this part is 30. Okay. So this is a resultant. So the resultant is has become that. So pi r is equals to 2 into. So both the magnitudes are same. So 2 into under root of 3 by 2 pi maximum into cos of 60 by 2, which is equals to 1.5 pi maximum. Okay. So here it has been given the vector diagram. So case 2. Here, when theta is 60 degrees at this point. So what happening here, pi b is 0. Directly we could know from the waveform. Okay, so pi b is 0. And yes, what is positive direction? Pi r. Pi r is positive direction and it is root 3 by 2 pi maximum, and pi y is in negative direction and it is minus root 3 by 2 pi maximum. So both are same as before. So here pi y is in negative direction, so we are considering in this direction. So here is a pi y and the pi r is positive, and the resultant will be this part. So this is pi maximum by, that is 1.5 into pi maximum. Otherwise we can tell that is 3 by 2 pi maximum, or else 1.2 pi maximum. Okay. So at position at when theta is 120 degrees. Okay, the theta is 120 degrees, this point. So here pi y is 0, yes, and the pi r is positive, root 3 by 2m, and pi b is negative. So the vector diagram at theta is equals to 120 will become, so this is a vector diagram at theta is equals to 120. So this is positive and this is negative, and the resultant pi r is 1 by 2 pi maximum, that is 2 into root 3 by 2 pi maximum cos of 60 by 2. So in the same way at 180 degrees. So what will be the pi r at 180 degrees? So here at 180 degrees we observe pi r is 0, pi maximum in negative, and pi r is in positive, and the resultant pi r is 1.5 into pi maximum. Okay. So this is pi y is positive and pi b is negative, and this is the resultant. This has been calculated as same as previous. Okay, so it has been observed from this part to this part. Everywhere the resultant flux is 1 by 1.5 pi maximum, that is 3 by 2 pi maximum. Okay, fine. We will see at 240. What will be at 240? At 240 also pi b is 0, pi y is positive, and pi r is negative. So, and small pi r, that is resultant flux, is 1.5 pi maximum. So this is the vector diagram, and at 300 degrees, like previous only, we have to find out pi r is negative, pi y is 0, and pi b is positive. So the resultant flux is 1.5 pi. So here in all degrees, what we are observing that at everywhere till 360 degrees, till 360 degrees, step by step, we could able to find out the resultant flux is 1.5 pi maximum only. Okay. So here if we observe the resultant flux direction also has been given. Okay. So this is a resultant flux direction, and this is a resultant flux direction. The resultant flux. So what's happening? The resultant flux is also rotating in a 360 degrees. The resultant flux is also rotating 360 degrees. Hence, we conclude that the resultant flux is of constant value at every point. So pi r is equals to 3 by 2 pi m, which is equals to 1.5 pi m. So the resultant flux rotates around the stator at a synchronous speed given by ns is equals to 120 f by p. So here, if we observe that, so this is an animated part. So in the rotor, we have excited. The rotor is separately excited with a DC supply external, and once we have given a supply to an AC, so as the current passes, so here we can see in the phase A, phase B, and phase C. Okay, this is a current, and as the current flowing, the same way the flux will flow. And once the current flows, the flux generates, and the flux will form a resultant flux, which is a rotating flux we have observed in 360 degrees, and what direction it has been rotating and how it is rotating also. So a resultant rotating magnetic flux with a constant magnitude has been formed. So this is the so there are two graphs which is giving a rotating magnetic flux with a simple wave. So here if we observe each and every degree, what is the rotating flux, how it is rotating has been given. Okay. This is the rotating flux it is rotating. We have to consider only the resultant flux here. And this is a vector diagram. So as before, the positive direction of the flux spaces have been shown separately in figure 5b. Arrows are these flux spaces are reversed when each passes through 0 and becomes negative. So mathematically proof. So taking the direction of flux due to phasor 1 as reference direction, and we have pi 1 is equals to pi maximum cos theta, that is 0. Okay, cos 0 plus sin 0 sin of omega t, then pi 2 is equals to pi maximum cos 240 plus sin 240 sin of omega t minus 120, and the pi 3 is equals to pi maximum cos 120 plus cos plus sine 120 sine of omega t minus 120. So expanding and equating the above equations, we get that pi r is equals to 3 by 2 pi maximum sine omega t plus j of sine omega t, that is 3 by 2 pi maximum 90 minus omega t. So the resultant flux is of constant magnitude and does not change with time. So it is constant. So in this session, we have learnt about the rotating magnetic flux and how it is produced with a three-phase supply, and the mathematical proof also which is producing the rotating magnetic field. And also we discussed about AC motors, classifications of the AC motors with a different depending upon a different factors, and comparing the with a synchronous motor, and we have found the advantages and disadvantages of a synchronous motors also, and applications of synchronous motor. So we will see some best points here. So synchronous motor is a constant speed motor. Yes, it is a constant speed motor. And the overexcited synchronous motors works with leading curve factor. Overexcitation synchronous motor will always works with leading curve factor, not lagging curve factor. Okay. Synchronous condenser is a synchronous motor with overexcitation. Okay. Synchronous condenser is a positive that is leading curve factor. It is overexcitation. The rotating magnetic field is produced by three phase. Yes, even two phase also. The speed of a rotating magnetic field is given by Ns is equals to 120 F by T. The magnitude of the resultant flux is given by 1.5, the maximum value of the flux. So hope today's session and the topics we discussed has been interested to you. So we will meet in the next session with the constructional details and the working the principle of a synchronous motor. Thank you so much.